1.1.1.1 locally, corresponding to a MAC. That is, local at least, in addition to the current interface MAC. In addition to the parameters corresponding to the interface IP and MAC, there should be some other parameters. That is, next hop current traffic. It stands to reason that it was sent from here. Now it will have a problem. If you configure the next hop to tell R2 its datanet 192.168.1.2 send, then R2 tells R1 whose MAC to encapsulate. R1 encapsulates the MAC of the next hop. So if R1 wants to find its MAC, just send an ARP request. After it receives it, it will reply to R1. But now, the routing table doesn't tell R1 where to go. So whose MAC should R1 go to? Please pay attention. If there is no next hop, the router will choose to ask the MAC of 1.1.1.1. Because it's not telling it to go to 1.1 now. Next hop to go 1.2. Just tell it to send out from the 00 interface. Then it doesn't know it's going to 1.2 at all. So when it goes to ask the MAC, will not ask 1.2 MAC. The destination IP is marked as 1.2. It knows it's going to 1.2. It goes to request 1.2. If you do not mark this 1.2 for it, it only knows that it is going to 1.1. So now it asks for the address. It only requests the MAC corresponding to 1.1. It will send an ARP to ask who is 1.1. But this 1.1 won't give it a reply. Because of cross-network segment, ARP broadcasts can only reach the left interface of R2 at most. Now this lookback is another interface on R2. No matter which virtual interface it is, it must not be in the same network segment as it. Broadcast messages cannot be forwarded. So it can't get its corresponding MAC. It doesn't work. We can check. Show ARP. Check the current ARP on the device. First let me tell you. Why do we have this here? Because just before I configured, I just pinged. See if it works. So it will have. But it doesn't work if you ping. When you do experiments after class, after finishing, you can directly connect without testing. If you don't test the direct connection, you can't get this 1.2 locally. This will not appear in the appearance. You need to know this. But this does not affect our class. It doesn't work. That is, it does not ARP to the destination network. So the broadcast will only be sent here. Then according to the communication principle of ARP, when an interface of R2 receives an ARP packet, it depends on the target IP in ARP. Is R2 himself. Its destination IP is 1.1.1.1. R2 is 192.168.1.2. They are different. In theory, this packet should be dropped. Well, now it does drop the packet. So R1 has no way now. Get the corresponding MAC. Because R2 is not 1.1. So R2 will not respond to this ARP message to R1. Then R1 has no way to encapsulate the 1.1 MAC. R1 local data cannot be encapsulated at layer 2. Data cannot be forwarded normally. By default it doesn't work. But it has something to do with a command I just entered. I turned off the ARP proxy under the interface. Let's say Cisco's device. The ARP proxy function under the interface is enabled by default. So I'm going to turn them off first. You can see the phenomenon. So how can I make it pass now? Now let's test it again. It doesn't work. We can on the device R2 enable the proxy function of ARP for it. Let's take a look together. Enter the 00 interface. I turned on its ARP proxy function. The command to open this is as simple as IP proxy ARP. Proxy ARP. Open now. After opening, let me show you a rather miraculous phenomenon. I will ping 1.1 again. We can observe. It works now. And now, you can check the current ARP table. Now there is ARP to 1.1. But this is the MAC of 192.168.1.1. AABBCC002000. They just pinged each other. So it got its MAC. Let's see now. 1.1 MACs are the same as 1.2. For now are 1. When going to 1.1, it thinks that the MAC of 1.1 is the MAC of this interface now. That is, I have enabled the proxy function of ARP under the interface. When R2 receives an ARP message, if target IP is not yourself, but it turns on the ARP proxy, then this data packet R2 will not be lost directly. It depends on whether the local can go to the destination network segment. If possible, R2 uses the interface that received the packet now. Give R1 a reply. Then I will give you a reply now. Because this is one of its local routes, so it is reachable. It will reply to R1. R1 goes to 1.1. The next hop encapsulates R2's MAC. R2 to help R1 forward. Is there a 1.1 route on R2? Let's take a look. Show IP route. Okay. Has this route. This is a local route on R2. So R2 is reachable. R2 can help R1 forward. What the R2 gets is actually its MAC. You will find what we talked about today. Not quite the same as the previous two PCs. It used to be a router between two PCs. Today is two routers. For this thing, it is not fixed. That is, this is only true on Cisco devices. Cisco device interface. The ARP proxy function is enabled by default. So the same experiment. R1 and R2 configure the interface interconnection address. R2 opens a loopback port here. If R2 directly pings, the ping fails. That is, if I write static route here, refers to the current outgoing interface. Equipment from other manufacturers will not work. But Cisco devices can pass through by default. Check it out now on R1. Look at the routing table. I will now change it to a correct. We usually don't write. So I cancel the one just now. It's here. You can cancel before an O. For example, 1.1.1.1. I'll give it the cancellation just now. Then specify the next hop. 00. We cancel it. After cancellation. Now it doesn't exist in my routing table. Now I'm going to write a new one. Copy the previous. Except this. We directly write the next hop. Inside Cisco. Our command to configure the next hop is destination segment. Mask of the destination network segment. Add the IP of the next hop. Just write 192.168.1.2. Write it down and check it later. I now ask you a question. You see I'm in this routing table. Write a route to 1.1. The next hop